Well, you'll learn. You know. I'll begin with a prayer. So, dear Heavenly Father, I just thank you for this day. I thank you for these students. Just pray that you'd bless this class, help us to glorify you this semester and what we do, and just pray you give these students persistence and just courage to understand. And just, Lord, I just pray you'd lift up these students every day, Lord, as they work. In your name I pray, Lord Jesus. Amen. All right, so what is this course about? Well, this is linear algebra, right? And so what is linear algebra about? Well, it's, roughly speaking, you could say it's the study of linear equations, and that's not quite honest. Really, linear algebra is the study of vector spaces and their transformations. What's a vector space? Well, a vector space is some set which has some notion of addition and what we call scalar multiplication, all right? And then a linear transformation is a function that goes from one of these vector spaces to another and preserves those operations. We'll get there eventually, all right? That's where we're going. For the moment, we mostly study linear equations, how to solve linear equations and how to understand them in terms of matrix notation. So actually today I'll mostly focus just on what is a matrix, our notation for matrices, and how to prove things about them, okay? And I'm going to take a slightly more general approach than you might sometimes find in this course, in the sense that I'm going to set it up over what's called a commutative ring. So maybe you haven't thought about that before. So here's some notation. So first of all, z, this is the integers, all right? In contrast, n, natural numbers, all right? So that's 1, 2, 3, da-da-da-da. Some people throw 0 into the natural numbers. I'm not one of those people, all right? And then past that, of course, we have rational numbers, right? What's a rational number? Something like p over q, right? Such that p and q are integers. And what's the kind of pesky condition we need on q? Yeah, q is non-zero. So this notation I'm just using is what's called set builder notation, right? This bar is read such that. Now perhaps you've had another course where that's sometimes replaced with just a colon, right? I'll always write a bar for the set builder notation. What other sets of numbers are we interested in? How about real numbers, right? Real numbers, sometimes you'll see interval notation, minus infinity to infinity for that, right? Set of all real numbers. And what's past that? How about complex numbers? Complex numbers have the form a plus ib, such that a and b are what? Real numbers, and I squared is what? -1, right? But otherwise, you add and subtract complex numbers just like real numbers, right? And let's see here, what's the other number system we use in here a fair amount? I mean, well, that's not honest. We actually don't use this that much, but I have some token problems here and there, what are called z sub n, all right? And so what this is, it's the set of 0, 0 bar, 1 bar, 2 bar, dot, 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 n minus 1 bar. These are kind of funny things. These are the so-called modular integers, or let me just be specific to give you a sense of how this works. We'll start out real simple, z2. This has 0 bar and 1 bar in it. And the way this works is that essentially 2 is equal to 0 in this number system. We show you specifically, here's how we add them. If I have 0, 0 bar, 1 bar, 0 bar, 1 bar. If I look at addition, 0 bar plus 0 bar is 0 bar. 0 plus 1 bar is 1 bar. 1 bar plus 0 bar is 1 bar. 1 bar plus 1 bar is equal to 2 bar. That's basically the definition of this modular addition. And then the other rule in this number system is that 2 is equal to 0. So that's just 0 again. So to fill out this addition table, 1 bar plus 1 bar is actually 0 bar. All right. So 1 plus 1 isn't 2. 1 plus 1 is 0 in this number system. It's kind of interesting. You can also multiply these. Multiplication. 0 times anything is still 0. 1 times 1 is 1. All right, very exciting. Now, this notation gets really old really, really fast. So when I give you a problem that involves modular arithmetic, which is what I'm showing you, this is modular arithmetic mod 2, it's much nicer to drop the bars and just work with the understanding that you're working with these what are called equivalence classes of integers. I won't get into all that structure here because it doesn't really matter to us. If I was teaching Math 200, I might get into that, or Math 421. Some of you will experience, I imagine. So Z3, 0, 1, and 2, just drop the bars with the understanding that, for example, 2 times 2 is 4, but 4 is equal to 1, right? 1. And sometimes you might say modulo 3, right? So Z3, if we were to draw the multiplication table here, a little bit more exciting. 0 times anything is still 0. 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. But 2 times 2 is 4, which is 1 again. Right? Okay. So, you know, you guys think about time, and when we ask questions about doing things on a daily basis, that might, if you work with military time, you might be doing things modulo 24, right? Then if you're working with the 12 hours, maybe you're working mod 12. Questions involving mod 10 and mod 12 and mod 24 have existed for a long time, right? And if you start looking at those kinds of questions, you can find yourself trying to solve equations mod sum n. All right, anyway, I just need to introduce these. This is just an example. We're not really focused on understanding the structure of these. More or less, it's just a token example. One more example, though. I want to show you something that's weird. If we look at Z6, 0, 1, 2, 3, 4, and 5, dropping the bars because the bars are really annoying. Well, in this set of numbers, what's 2 times 3? Yeah, it's 0. Again, of course, mod 6. So this is rather different than my first two examples in the sense that we have the product of two things which are non-zero, and they gave me back 0. If you look at Z2 and Z3, that wasn't the case, right? Only 0 times something gave you 0. So this phenomena is what are called zero divisors. Right. In contrast, in here, if you look at the numbers which are relatively prime to 6, which numbers are relatively prime to 6? Ooh. No. Relatively prime to 6 means shares no common prime factor, right? I mean, so 1 and 5 are relatively prime to 6, right? 2, 3, 4, these all share common factor 0. So 1 and 5 are relatively prime, and if you look at it, so you know, what's 5 times 5? 25, which is what here? 1, right? So this shows that the multiplicative inverse of 5 is itself. So you could say that mod 6, 1/5, is equal to 5. It's kind of weird, right? Yeah. So your normal ideas about proportion and so forth don't really extend to this number system. It certainly wouldn't be reasonable to say that, you know, 5 pizzas is the same as 1/5 of a slice of pizza, right? I mean, 1/5 of a pizza is not the same as 5 pizzas, right? Well, that's because modular arithmetic is not the correct number system to talk about slices of pizza, right? Anyway, all right, enough. So what I mostly am doing this is just to give you some examples. These are mostly the number systems we use. We're going to take matrices. We're going to put these numbers in matrices and do things with them. So what's a ring? a ring R, all right, what this is a set paired with addition and multiplication. All right. So how do addition and multiplication work? Well, they work like you know. I mean, what's a plus b times c? What's that going to be equal to? Yeah, a times c plus b times c. What would let's see here. What would a times b times c be equal to? It would be equal to a times b times c, right? My English is letting me down a little bit here, but if you look at the board, you'll notice that I've actually said something. In other words, multiplication is associative. Well, addition is also associative. In other words, I can write a plus b plus c equals a plus b plus c without ambiguity. It doesn't matter if I put the parentheses here or here, we get the same answer, right? What else is there with this addition for the ring? There's something called 0 in the ring. 0 is the additive identity. How's that work? Yeah, a plus 0 is equal to a is equal to 0 plus a. So anything plus 0 on the left or the right is equal to itself again. Now some rings have an identity, a multiplicative identity, some don't. If the ring does have a multiplicative identity, we usually use the number 1 to denote it. So like 1 times a is equal to a again. So that would be for a ring with identity. Now addition in a ring is assumed. When you talk about an addition, by assumption, you have this condition, a plus b is equal to b plus a. So addition is assumed to be commutative. All right? In contrast, multiplication for a general ring may or may not be commutative. You can talk about rings where you have a non-commutative multiplication. In fact, the matrix multiplication that I'll soon define for you guys is such an example. A set of all matrices form a ring. Excuse me. Now, but if we have commutative, that means a times b equals to b times a for all a and b in the ring, then R is a commutative ring. All right. I'm mostly telling you this so that when I give you a homework problem where I tell you R is a commutative ring with identity, I want to let you know what that means. What does that mean? What are you entitled to as students? What data do you have to work with there? You have that there's an addition and that there's a multiplication. The addition is commutative. There's a 0. All right. There's a number 1 which multiplies anything to give back that same thing. And the addition and multiplication play nice together. They distribute like you're used to. You have this distributive property. The addition is associative. The multiplication is associative. All these wonderful familiar properties in a commutative ring with identity. What are examples of commutative rings with identity? Yeah. The integers, right? Very good. How about the natural numbers? Why is that not a commutative ring with identity? Yeah, we do not have 0, right? There's not the additive identity. It's not in there. The other thing I didn't say over here, but I should say, is that there's something called minus a for each a. So like minus a plus a is equal to 0 for each a in R. There exists. So my penmanship it kind of degrades as you approach this level. There exists minus a in R called the additive identity, additive inverse, right? We usually call it like minus. For 2, there's a minus 2, right? For x, there's a minus x, such that when you add the additive inverse to the element, you get back 0 again. That's part of what it means for it to be a ring. Okay. A large part of Math 421, after this course you take Math 421, is to actually understand these things systematically as part of a larger discussion. For here, right now, just a language, okay? So yeah, the natural numbers are not a commutative ring because they don't have 0, and also they're not closed under, there's no negatives, right? How about rational numbers? Is that a commutative ring? Yep. Real numbers? Yep. Complex numbers? If you add two complex numbers, you get another complex number? Sure do. Multiply them, how's that work? If I have 3 plus 2i times 7 minus 5i, what do I get? You get 21 plus 10 plus I times what? 14 minus 15, you know? So I get 31 minus I. So you multiply complex numbers in the usual way, just with the added rule that I squared is minus 1, right? I think you guys know this. Do you know that you can find the multiplicative inverse of any complex number? If I have 1 over a plus ib, what's that equal to? If I want to put it back in what's called Cartesian form. Just doing a brief review of the complex arithmetic you're supposed to know from high school, but many of us don't. Yes? Use the a minus ib, so I multiply by that upstairs. What happens when I multiply by that downstairs? Right. That's the point here. A minus ib over a squared plus b squared. Very good. And you can do that as long as what? At least one of a or b is non-zero. So every non-zero complex number has a multiplicative inverse. That means that the complex number system is what's called a field. All right? A field is a commutative ring with unity, which we usually use a 1 for the unity, such that every non-zero a, let's call the field F, non-zero a in F has a inverse in F such that a inverse is equal to 1. In abstract algebra, when there exists a multiplicative inverse, then we say such an element is a unit. So another way of restating what it means for it to be a field is to say a commutative ring with unity is a field if every non-zero element is a unit. Many of the examples I put on the board here are fields. If a rational number is non-zero, what's its multiplicative inverse? P over Q has multiplicative inverse what? Q over P, right? Real number, well, you kind of know it. What's the multiplicative inverse of pi? 1 over pi, right? I mean, yeah. But I just showed you how to find the multiplicative inverse in C. Now, these are a little bit sneakier, right? What's the multiplicative inverse of 1 here? Well, actually, the multiplicative inverse of the unity better be the unity always, right? That's kind of part of the package here. But on this one, what's the multiplicative inverse of 2? It's 2 again, right? It's its own inverse. That can happen in the modular arithmetic. So Z2 is a field, Z3 is a field, because every non-zero thing, there's just one of them. The unity is the only non-zero thing. It's a unit. Here, 1 and 2 are the non-zero elements. They're both units. 1 inverse is equal to 1, 2 inverse is equal to 2. Z6, is this a field? It's not a field. The fact that 2 times 3 is 0 means that 2 inverse and 3 inverse doesn't exist if you study this more carefully. You can suppose that if you suppose there was a unit, you could find a contradiction. Anyway, so Z6 is not a field. And in fact, generally speaking, when you study this more deeply, you can prove that Z mod a prime is a field. Z mod anything else is not a field. So Z6, Z4, Z10, Z20, whatever, not a field. But Z3, Z2, Z5, Z7, Z11, Z13, Z17, Z19, Z23, I don't know, you go on. You got the, you number theorists, you can tell me the primes. But those are all fields. Now this is important because when we solve equations, we're going to learn Gaussian elimination. We're going to learn how to do Gaussian elimination with respect to a field, all right? Gaussian elimination won't make sense with respect to just a plain old plain Jane commutative ring because we have to do division in the Gaussian elimination. But we can do Gaussian elimination for a field. So that's why I'm talking about this right now, so we are all on the same page for this terminology. All right. That's pretty much all I've got to say about chapter 1. So we're going to move into chapter 2 now, which is on matrices. All right, so what is a matrix? A matrix over a commutative ring R is M by N if it has the following form. So what do you want to call the matrix? Want to call it, we can call it A. So here it is, A is equal to, so we put A11 up here, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So this is what a matrix is. It's a rectangular array of elements from a ring. Now, you're like, well, I don't see why that should have anything to do with a ring. Couldn't you talk about a matrix of other things, like things where you don't have a well-defined notion of addition and multiplication? I mean, sure, you could. We could take like the matrix of students in here, right? I'm not sure how to multiply two of you, you know? I mean, there's not necessarily a well-defined operation of multiplication. Like, I don't know how to take two of you, multiply you together, and get another one of you. I mean, maybe you know each other more deeply, so you have some sense of like what a good joke would be in terms of that regard, you know, but I don't know enough, so. Although my dream is to concoct some fictional romantic relationships going forward. I feel like I've let down the students of this current generation by not doing this. Like in the past, I set forth certain fictional relationships and insisted on their existence. It was a lot of fun, but I haven't found a good fictional relationship to promote yet. I'm looking though. So my point is this notion of matrix is really the same as the notion of an array, which is just kind of a doubly indexed list. The point is you have rows, you have columns, you have ways of distinguishing between the two. If you have two different matrices, they're only going to be equal if they match in every single one of the slots. So this is just the natural sort of generalization of what we talked about as a vector in calculus 3 or 2. Well, 3. Oh, let's not start. I get sad when I realize some of you hadn't had calculus 3. Show of hands who've not had calculus 3. It's not your fault. It's a stupid school. Anyway, sorry. It's not even the school. It's it's the government. Yeah, blame the government. That's safe. And it's from before Trump, so we can blame Obama. Let's see here. So, no, I have to blame the misplaced priorities of education curriculum in this country. But anyway, the point is, if this is M by N because there are M rows and there are n columns. All right. Sometimes you'll see this notation, A equals to Aij. The brackets here are not like, oh, write them if you want to, don't write them if you don't want to. No, not writing them makes you wrong. All right, those brackets are not optional. See, because in contrast, Aij is an element of the ring. All right? This is the ijth component of the matrix A. All right? And that I, and that's what? For what? 1 less than or equal to I, less than or equal to blank, and 1 less than or equal to j, less than or equal to blank. You fill in the blank for me. I is the so-called row index, right? See, because if you look at a particular row, it's got the same I across the whole thing, right? Like the first row has I equal to what? Yeah, I equal to 1, right? And this is I equal to m all the way across. Yeah. So m. And for the matrix under consideration right now, the one we're talking about here, j is the row index. Excuse me. Good grief. Sadness. J is the column index. It ranges from what? This would be j equal to 1, right? 1, 1, 1, 1, 2, 2, 2, 2, n, 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 n. So j ranges from 1 to n. Okay? Now, you can also look at the matrix in terms of, you can look at it as a bunch of columns glued together. It's like column 1 of A, column 2 of A, column n of A. It's the concatenation, or you can think of it as the glue. You can think of a matrix as a bunch of columns glued together to make a larger object, right? Or you can think about it as a bunch of rows glued together, right? So I can also look at this as a stack of rows. It's like row 1 of A, row 2 of A, row m of A. All right, so let's see if you understand. And now, naturally, you also want a name for the set of all matrices over a commutative ring. The notation I use for this, set of all m by n matrices over R is, what I call it, is R m by n, right? So this is the set of m by n matrices. So in particular, I can say that A is an element of R m by n. Make sense? Okay, well, if you understand this, you should be able to tell me column, what's the jth column of A is an element of what? The ith row of A is an element of what? R what? One by n. This one here? I think we're looking for n by 1 because look at it. It's got one column, right? Like the jth column is just this one column, but it's got m rows. Oh, wait a minute. M rows, huh? Oopsie. Did you say m by 1? You don't remember? Yes. Now this one would be 1 by n, right? Because each row has n entries. So anyway, a column vector, right? So this is the set of column vectors. Column vectors length m. Right. All right. Let me continue in this litany of notation for you guys for just a minute. Definition. Rn, we'll say Rm here. What I say that is well, it's x1, x2, xm, such that x sub I is an element of R. But in fact, this is just a sneaky notation. What I really mean is Rm by 1. And so you're like, well, what are you talking about? So here's what I'm talking about. This notation is a shorthand for this notation. And it is not equal to, notice the difference here. This is a row vector. This is a column vector. That on the left here, this is my sneaky hidden column vector notation, all right? You're like, well, why would you do such a thing? Why not always just write columns? Because when you're writing paragraphs of text, and you have a 5-component column vector, you really don't want to take up 5 lines of text for that one column vector, right? So it's important for us to have a nice compact notation for column vectors, which is written horizontally. It's just a point of language. You're like, this doesn't seem like a lot of math. It just seems like a lot of notation. That's right. Linear algebra is a lot of notation. Learning notation is probably 50% of what you need to do in here. And that's a lot of what linear algebra is. It's finding good notation to express complicated problems. So if you're just like, well, that's just notation, I don't want to care about that, well, then you are doomed to failure in here. You need to care about the notation. Notation is linear algebra, a lot of it. Any questions? Okay, so we have these matrices. The next question is, when are two equal? So essentially, this is the definition of, I mean, I really can't answer this without getting into minutia that you guys don't want to see me get into. I mean, to answer this, I'm going to make it a definition. A and B in Rm by n, then A equals to B if and only if Aij is equal to Bij, let's say for all I and j. When I say for all I and j there, what's that a shorthand for? What's this a shorthand for? For all I comma j such that what? Like we were just talking about, I ranging from 1 to m, j ranging from 1 to n, right? I mean, you could prove, if you had you can construct matrices from sets of sets of sets. You can actually use set theory to build matrices from scratch if you're interested in that sort of thing. I don't think that's really that interesting for this class, so I'm not getting into all that. Okay, so what else can we do with matrices? Can we add them? What do you think? Right. Oh, hey, I buried something I should have written in here somewhere. What do we say if m equals to n? It's a square matrix, right? And I also told you about these are special kinds of matrices too, right? That's a column vector, which is a specific special kind of matrix, right? And this is also what's called a row vector, right? But both row vectors and column vectors are, of course, special cases of matrices. We also, at times, will just identify the ring itself as a 1-by-1 matrix. But here's the definition. If A and B are in Rm by n, then A plus B is an element of Rm by n, defined how? So A plus B, ij, all right? That means we're looking at the ijth component of this new object. By definition, what is it? Right, Aij plus Bij. Very good. So, example, if I take A, an n by n matrix over some ring, it could be a real, complex, rational, whatever. And if I let zero matrix, how would I define that? What should the zero matrix be? How about this? 0ij is equal to 0 for all I and j. Is it okay with you guys if we adopt the convention that when we say for all ij for a matrix, it's understood that I and j should range over the appropriate ranges? I think you'd like that convention, right? As opposed to being forced to write out all this over here. Now, there will be places where you need to write this out because that's the whole point of the proof, to sort through those things. But when it's not so interesting, like here, let's just say for all ij. What happens if we take A plus 0? By definition, that's Aij plus 0ij, right? Which is, well, I just told you that's Aij plus 0, right? Which is just Aij, right? Because 0 in the ring added to anything gives you back the anything. Right? What's this show? A plus 0 is equal to A again. Why? Because we've shown A plus 0 and A have all the same components. Right? That's what it takes to show two matrices are equal. Now, what do you think properties of matrix addition are? I guess I should also throw another definition in here. What if we have a constant in the ring and A an m by n matrix? What would we mean by CA is also going to be an m by n matrix, right? With what? How are we going to define CA? What's the ijth component of C times A going to be? Yeah? Cij, you mean C times Aij? Right. That's the definition of scalar multiplication of a matrix by a scalar. A scalar is just a word for a number in the ring. So it's relatively simple to prove that this set of matrices, right, has a pretty natural structure with respect to this addition and multiplication, right? So assuming R is a commutative ring with identity, we have the following, right? Like A plus 0 is A again, right? And I think you can easily see that we could just as well have proved that 0 plus A was A, right? What if you did A plus B? Wouldn't that be equal to B plus A? Right? In fact, that's the homework problem, to prove that. Right? What if we had a constant times A plus B? What would that be? Yeah, CA plus CB. Let me prove that. So I have C times A plus B. We'll stop with this for today. C times A plus B, ij, right? So to prove this, again, what am I assuming? A, B are in a commutative, the matrices over a commutative ring, and C is a scalar in the ring. So to prove item 3, I need to show that those two things are equal for every component. How do I do that? I look at C times A plus B ij, right? That's what? That's equal to C times A plus B ij. And over here I write, by definition of scalar multiplication. I guess I should have told you guys this right here is what's called scalar multiplication. Definition of scalar multiplication. What's my next move? My next move is that this is C times Aij plus Bij. Why? Definition of matrix what? Addition. Matrix addition. This is how we define matrix addition. The ijth component of the sum is the sum of the ijth components. Now, I use the generic properties of a ring, which is that we have this distributivity. C times Aj plus C times Bij. Right, this is just basic R is a ring. Okay, that's ring arithmetic. And then what do I do? Go, oh, okay, well this is Ca Ij plus Cb Ij. Here it again is definition of scalar multiplication, right? Now how do I combine those two? Factor, right? Oh, I mean, I can rewrite this. This is really Ca plus Cb Ij by what? Definition of matrix blank. Fill in the blank. What did I use going from the step above to the step below? What definition am I using? Definition of matrix addition, right? See, because the sum of these two matrices is equal to this. The ijth component of it is. And then that proves number 3, right? Because now I've shown that C times A plus B is equal to Ca plus Cb. Every component, arbitrary ijth component matches, therefore these two things are equal. That's how you prove these sorts of basic identities. All right? So next time, I'll probably define how to multiply matrices, and we'll look at some more, we'll actually start looking at things with actual numbers in them and so forth more so, and hopefully start talking about linear equations sometime very soon. So thanks, guys. Did I actually hand the attendance sheet around? Okay, make sure that gets back to me, otherwise I'll be fired or something. I don't know. I'm not sure what happens if I actually don't take attendance. Let's just not find out. Oh, addition. Addition. I'm sorry, I said it, I didn't write it. There's a wait list?
Yes.
There's no wait list. They dissolve wait lists, right?
But I just added today.
There's a wait list again?
I think.
I'm very confused. Tell you what you should do. That's annoying. Just email me your student ID and what you want to do, and then I'll forward it to the registrar. Hopefully they'll actually add you.
All right, thank you very much.
Yeah, I don't mind.
I really have to.
There's definitely room for you in here, so it's fine.
Right, thank you.
Yeah. Assuming you have prerequisite, what do you?
I'm sorry?
What have you had the math 200 or 250?
Yes, I did. Yes.
Okay, excellent.
Thank you.
Oh, exciting.